Now we are ready to prove the following weaker version of prime number theorem due to Tchebyshev, which states that pi of x grows at the same rate as x divided by log of x as x goes to infinity. Although we cannot infer from the theorem that pi of x divided by this quantity goes to 1 as x goes to infinity. In the first place, let us establish the lower bound for pi of x. The definition: theta of x is the sum of log of p's with p less than or equal to x. And now we're going to measure this sum by considering the maximum of log of p's. Log of p's here can be upper bounded by log of x. And when we pull out the log of x from here, the rest will be bounded by the sum of 1s for p less than or equal to x, which is precisely pi of x. However, it follows that pi of x, which is bigger or equal to theta of x divided by log of x. But the theorem for 15 we just proved, which states that theta of x is asymptotically equivalent to x, and in particular is bounded with some constant multiple of x, and now we divide by log of x. And this proves the lower bound for pi of x. Namely, pi of x is bigger than some constant multiple of x divided by log of x. On the other hand, to show the upper bound, we take delta, the number between 0 and 1. From the definition, if we make a truncation at p equal to x to the 1 minus delta, if we take the following truncation, we get an inequality. And this can be bounded below if we replace log of p by x to the 1 minus delta, which is 1 minus delta times log of x times the summation p from x to the 1 minus delta to x. And we simplify this. Using the definition of pi of x, the sum is equal to pi of x minus pi of x to the 1 minus delta. And the last line can be further bounded below by now we can simply replace this pi of x to the 1 minus delta by x to the 1 minus delta, because it is obvious that the pi of something is less than or equal to that something. So from here, we solve for pi of x. What is pi of x? Pi of x is less than or equal to theta of x divided by 1 minus delta log of x plus x to the 1 minus delta. So this is what we can solve from this inequality. And these two terms can be upper bounded by, first, observe that theta of x can be upper bounded by some constant times x. And for the second term, x to the 1 minus delta, we claim it is bounded by some constant times x divided by log of x. This is because log of x grows slower than x to the delta. So this part is by theorem for 14, and this part is by the fact that log of x grows slower than any positive power of x. And these two terms together is just some constant multiple of x divided by log of x. And this establishes the upper bound for pi of x. So now we can summarize, and this finishes the proof for the Tchebyshev theorem. The proof of the Tchebyshev theorem also gives us the following relations between pi of x, theta of x, and psi of x, which reduces our job of establishing the prime number theorem to establishing that theta of x and psi of x are similar to x when x goes to infinity. To prove these relations, we first observe that by theorem for 13, which states that the difference between theta of x and psi of x is big O of the square root of x times log of x squared. And by theorem for 14, theta of x and psi of x are both asymptotic to x. Although we don't know if the ratio of theta of x divided by x or psi of x divided by x converges to 1 as x goes to infinity. From theorem for 13, we know the limit as x goes to infinity of theta of x minus psi of x divided by x is 0. And if you divide both numerator and denominator of x, the numerator will become theta of x divided by psi of x minus 1. And denominator will be x divided by psi of x. So this means the limit as x goes to infinity of this quotient is equal to 0. But this denominator from theorem for 14 is bounded below and above by two positive constants. Therefore, it forces that the numerator also goes to 0. In other words, theta of x divided by psi of x has limit 1 as x goes to infinity. And this proves this part of the relation. So now it suffices to prove that pi of x is similar to theta of x divided by log of x. In order to prove this relation, we recall two inequalities we established from the proof of Tchebyshev theorem. The first inequality is that theta of x is less than or equal to log of x times pi of x. And the second inequality is that theta of x is bounded below by 1 minus delta times log of x times pi of x minus x to the 1 minus delta for any delta between 0 and 1. So let me copy them here. And combining these, we obtain that pi of x times log of x divided by theta of x is bounded below by 1 and above by. So these two are just a straightforward computation from these two inequalities. Now for any epsilon greater than 0, we choose delta greater than 0 such that 1 over 1 minus delta less than 1 plus epsilon divided by 2. So as long as delta is small enough, this inequality must be satisfied. Since theta of x is asymptotic to x by theorem 414, we can choose x0 depending on delta and epsilon, which in turn only depends on epsilon, because this delta is chosen to be dependent on epsilon only, such that for any x bigger than x0, we have this guy. If we break it up, you will see write it as the product of three things. This part is bounded, this part is a constant. But this part, as x goes to infinity, it goes to 0. So as long as we choose x0 to be large enough, the product of these three must be less than epsilon divided by 2. And if we combine this part with this 1 over 1 minus delta, which is less than 1 plus epsilon divided by 2, you will see that this guy is squeezed between 1 and 1 plus epsilon divided by 2 plus epsilon divided by 2. For all x bigger than x0, which is something that only depends on epsilon. And now by the definition of limit, we have the limit of pi of x times log of x divided by theta of x is equal to 1, which means by our asymptotic notation, pi of x is similar to theta of x divided by log of x. And this finishes the proof of theorem 420. Now, as a byproduct of Tchebyshev theorem, let us establish the following. We let P1, P2, and so on be the list of primes in increasing order. Then, what is the size of the nth prime in this list? Tchebyshev theorem will tell us the size of the nth prime will be roughly n times log of n. And now let's prove this. First, by the definition for p sub n, because p sub n is the nth prime, we must have, by definition of pi, that pi of Pn is precisely n. Namely, there are precisely n primes less than or equal to the nth prime, which, by theorem 7, is bounded about by some constant times p of n divided by log of Pn. So this is by theorem 7, and this is by definition. So p sub n is bounded below by some constant times n times log of p sub n. So this a here, remember, as an unspecified constant, is different from a from here. In this situation, actually, this a here is a reciprocal of the a here, but we are going to use the same letter anyway. And how is this guy compared with this guy? You should be able to immediately realize that p of n is actually bigger than n, because the nth prime must be bigger than the nth positive integer. So this establishes the lower bound for p of n regarding this asymptotic relation. On the other hand, we also have that n, which is equal to pi of Pn, is bigger than some constant times p sub n divided by log of p sub n. And here comes the tricky part. We're going to split this as square root of p sub n times square root of p sub n divided by log of p sub n. It follows that the square root of p sub n is bounded above by some constant times log of p sub n divided by square root of p sub n times n. But p sub n will go to infinity as n goes to infinity, and log of p sub n will grow slower than square root of p sub n. So they together is less than some constant times n. And this implies that p sub n is bounded above by a times n squared for some unspecified constant a. And hence, p sub n, which is from this inequality bounded above by a times n log of p sub n, and so let me mark. So this is from here, and in the next step we're going to use this inequality to bound it again by some constant times n times log of n squared, which is again some constant times n times log of n, by moving this exponent to the front. And this completes the proof of theorem 8.